we have three steps for budget. The first step, no, three cases. The first case is just associative algebra. We have just associative algebra with unit over some commutative ring. Then we have the following thing. Yes, we can consider, as I said before, in cheating interpretation. Yes, in cheating interpretation we can consider free, maybe, free product of my algebra and polynomial algebra. Yes, and now I can define degree of epsilon is, I don't know, for example, minus 1, and differential on epsilon is unit. Then by Leibniz rule, this differential uniquely extended to differential on this algebra, associative algebra, and I obtain differential algebra and differential graded algebra, in fact, because in fact I have grading. Then I can identify the thing with tensor product, because what the element of this algebra is just some word, just a 0, some epsilon in some. I have some element a, then some power of epsilon, then some b, and so on. But if I have some power of epsilon, then I can consider it as epsilon unit, epsilon unit, epsilon unit. And so in fact I have epsilon 0, epsilon, then a1, epsilon, so on. Видите, я даже не тензор, я вообще epsilon использую символ. Okay, so I can identify the n-graded component of this associative algebra with tensor product of n copies of A, of n plus 1 copies of A. Yes, what?
Why can we always write that n equals 0?
What?
You wrote instead of epsilon to the power of n, just epsilon.
Uh-huh.
Why can we always do that?
Why it begins with A? No, because if it's epsilon, then it's unit. And if I have epsilon square, I consider it as epsilon unit epsilon. No, free product is free, but I have that unit here and unit here as the common unit. And I can just write unit in the middle, okay? So in fact, any word uniquely can be written in this form. And so I obtain that this is isomorphic. So this how differential works? This differential. I have differential on A is no differential. Differential on A is always 0. And differential of epsilon is a unit. So differential of this word by Leibniz rule works on the following way. D of A is 0, then D of epsilon is a unit. So I obtain epsilon 1, epsilon. Then I interchange D and epsilon have degree -1, and A have degree of 0 always now. My A is not graded. I have only one graded element is epsilon. So if I interchange this epsilon, the first epsilon D, I obtain minus. And then I have epsilon A2. No, and so on. It's the common, our usual bar differential. If I identify this with a bar, then I obtain, if I identify it, then I obtain this bar notation or tensor notation. And so on. So in fact, my graded algebra is with differential have the following form. I have my ring R. No, sorry, I have no ring R. Yes, I have my A. I have A tensor A. This is just the first differential is just multiplication because D of A tensor A is just multiplication. It's my multiplication, the first differential, and then from 3, it's my 0 graded component, the first graded component, and so on. This is epimorphism because I have unit. Okay, and this is acyclic chain complex, cochain complex, because it's contractible. I have contraction homotopy is just multiplication by epsilon. No, in this notation, it's just multiplication by epsilon because if you have graded algebra, when the unit is coboundary, then any element is coboundary. And if I consider, for example, left multiplication by epsilon, then differential is d epsilon is unit. It's x. Then d epsilon on x. So minus epsilon dx. So I obtain that d epsilon something plus epsilon d something is just x, just identity. So left multiplication by epsilon is just homotopy between identity and 0. So this chain complex is contractible. So it's acyclic. No, in this notation, this homotopy is just adding unit from the left. Chain homotopy adding unit from the left. And from this equality, you can check that this is homotopy between identity and 0 in this chain complex. So the chain complex is contractible, so it's acyclic. Okay. Now, if we consider ideal here, I can consider ideal generated by epsilon squared. Epsilon squared. Now you can check that this homotopy preserves this ideal. So in fact, no, this ideal is all, this algebra is all, and differential preserves this ideal, and yes, differential preserves this ideal. This is differential ideal. So this is also a cochain complex, and this homotopy preserves this ideal. So in fact, this is also contractible cochain complex, and so I obtain contractible subcomplex of contractible complex. So I obtain the following. Oh yes, I have following. The following thing. What is this subcomplex? It's just subcomplex consists of such in tensor notation or in bar notation is of such form where I cannot use epsilon squared. Now, what does it mean? This means that what if I have no, this means that. Oh, sorry, not where I. This means that in. This means that in each word, I must have epsilon squared. But epsilon squared means that I have unit in the middle. This means that in fact I have unit in the middle. So in tensor notation, this means that it's subcomplex generated by words with unit in the middle. And that's also contractible subcomplex. And what's the quotient? Now here, let me assume that my algebra is augmented. I have augmentation. I have inclusion of unit. And if inclusion of unit have left inverse, it's augmentation. It's inclusion of unit, it's augmentation. Then I have augmented ideal. No, and here I consider all my words and consider quotient modular words where I have unit in some middle term. Now this means that quotient is generated by words where in the middle terms I have anything except of units. No, it's exactly this ideal. It's quotient by unit. It can be identified. So this thing in tensor notation can be identified with bar construction where in the middle I have augmentation ideal. So this is this thing where in the middle I have a bar. This is no, yes. Let's I don't know. Let's fix some notation. This was this thing. It's bar construction for a over a, and this is reduced bar construction of a bar a. No, or maybe yes bar. Okay. this is 2, and this is Cauchy complex is also acyclic because it's also contractible. No, so because, no, sorry, it's not contractible, but it's, no, it's short extra sequence of chain complexes, and so quotient of two acyclic complexes is also acyclic by long extra sequences of homology, okay? This is acyclic, so this is also acyclic. So this is also acyclic, it's exact cochain complex, okay? Okay? What? Now, if we have, ну, maybe сейчас. So, нет, давайте больше. Значит, yes, what about if I consider now, let me have that n is left A module now. Left A module. And I want just tensor with this exact sequence by n from the right. Yes, and maybe one important thing that all these differentials of Cauchy complex, I can consider these things as left or right A modules, yes, from the multiplication from the left and from the right middle term. And from formula, it follows from that because dA is 0, so Leibniz rule means that differential is linear with respect to left or right multiplication by A. It follows from this that this is dx and this is also because my gradient of my A is 0 in my ungradient situation. So my differentials are A linear. It's maps of left and right modules. On these things, it's in fact AAB module structure. I have left module structure, right A module structure, and they commute with itself, so they do not intersect. So this is in fact AAB module, or left or right module. So let's consider this thing as chain complex of right A modules. I consider left A module, and I tensor these right A modules from the right by left and A module. Okay, what I obtain? I obtain this such sequence. No, yes, of course. If I consider, if I tensor something which ends by A, and I consider this as A module by the right term, and then I consider tensor product over A with n, then it's goes away. Yes, it's over R, then A over A. So if I tensor it over A by n, I obtain these things. Okay, do you agree? If I have something which ends by A, and I consider this as a right A module from this term, and then I tensor it over A by some left A module, then it goes away. So in something like this. This is notation, it's BAAN. No, and bar version.
What do you mean by bar?
No, if it's augmented, then it's augmentation ideal. It's kernel of augmentation. If you have inclusion of unit, and maybe you have left inverse to the inclusion of unit. It's augmentation. It's left inverse to inclusion of unit. Then a bar it's kernel. Maybe yes. It's maybe you don't need kernel. Sorry, maybe it's not kernel. It's just no. You don't need this. It's just a quotient by unit. So you don't need the augmentation. Sorry. It's quotient. It's quotient by unit. Unit is yes, you don't need that. It's direct sum until even. It's just okay, that's this thing. Maybe I'm not sure. Maybe for this identification you need that it's direct sum, and this is the same thing that you have augmentation. No, something like this. Yes, something like this. maybe for simplicity you have, no, in our case we have, our algebras are graded and this is always a direct sum and this is just augmentation ideal. Okay, what I want to say that this, now it's chain complex of left A modules. Все еще. No, because, no, yes, it's chain, it's no chain or co-chain if it's in positive degrees, chain complex of left A modules, and it's also exact. It's also exact because no, this homotopy, adding one unit from the left works here as well. Formula for differential is the same formula where I have just my words ends by element n on the right. And formula for homotopy is also the same formula and all works as well for this. So in fact, yes, I have something like, I have n. It's and the last term is plus minus n minus 1 n. Oh, sorry, n. Okay. And this homotopy also works and give you a contraction of this chain complex. This contractible chain complex, so it's contractible. And again, you can consider subcomplex where you have you always have unit in some middle term. It's also contractible, and you can consider bar quotient, and this is also acyclic complex. Okay. Okay. So it's contractible, it's acyclic. And now, so we have some exact sequence of left A modules which ends by n. So it's kind of resolution, maybe, but no, it's not obvious that it's free. And no, in general, maybe it's not free modules, yes. No, but what now if no, I don't know. No, if A is projective or free, okay, projective R module, and n. Sorry, yes, no. Нет, n is also projective R module. For example, if we overfilled, if our graded minimal R ring is filled, then it's also always true. If they are projective over R, of course, n maybe it's not projective over A, but if they are projective over R, over our unit ring, no, then no, then what? For example, unreduced thing. No, then these things they are if they projective. No, yes, no. Yes, they are projective. It's projective A module even. So I think this is no. Okay, let me assume that they are free. For example, we overfilled. If they are free, then these things, no, just free models is also free because the product of free models is free model. Okay. This is true. Then this is free module, and so if we consider free R module and tensors with R of A, this is free A module with the same basis. So it's free resolution. Then this thing is free A resolution of n. No, and A bar. If it's free and, for example, no, it's you have some augmentation. If it's direct sum, no, I think it's no, yes. If it's direct sum, then if A bar is free also, then bar resolution also free resolution. Okay. For example, if we overfilled, then it always works. Okay. So we obtain some, no, functorial, some I don't know, canonical standard resolution for any model over any ring, over any algebra over any field. For example, if we consider algebras over a field, then we have this standard bar resolution. So, for example, if we consider some right M module and tensor it from the left by M module, then we obtain chain complex which homologies are Tor. It's called what? We obtain something like this. Or bar here. It's called two-sided bar resolution or reduced. And this chain complex, it's homologies. It's Tor. Differential works by the same formula. Because in this formula, if I have, for example, M, A, N, I exactly need have right multiplication by M and left multiplication by A, and so on. So this chain complex computes your Tor. If you consider home to some left module M, well, then you obtain dual differential. Maybe we will discuss this on the next lecture for group homology. No, you have dual dual differential, you have home, and they compute X. Okay? Okay. Now, graded case. When A itself is graded. No, this is the same case, but we have signs. But these signs are just regular Leibniz or Kasul signs. The second, it's graded. Non-negatively graded, connected algebra. Connected algebra. Now then I also can consider this free product, and now, yes, epsilon is -1. But now I have differential on epsilon's unit, but also I have some differential on elements of, I don't. But now I have some gradings of elements of A. So grading of A is not 0, it's some grading, some elements, some numbers, okay? It's not 0 now. So, for example, if I have some word, then by Leibniz rule it's d of A is 0. But when I interchange D and A, I have some sign. So in fact, it starts from sign A 0, and then D epsilon. D epsilon is unit, so I obtain 1. Then I interchange D and epsilon again -1, then again 0, but again sign of A1. So I obtain minus сейчас, что я хотел сказать? Да, D. Сейчас. Так, все, я завис. Сейчас, когда мы... Сейчас, секунду. Ну да. То есть там просто навесится еще один знак. Правильно? And so on. То есть I have signs here. No, in tensor notation is the same thing with tensor notation. Okay, and again, because of this sign, because it's just Leibniz rule, you can check that it's differential squared 0. And again, you have epsilon squared. You have graded thing. You have such things. No, for example, for any n, you obtain the same thing. If you ends with n, you have bar think it's also contractible with the same homotopy. And bar is reduced bar resolution is acyclic because it's quotient of two contractible complexes. Okay? No, we just have signs, but this signs is just Leibniz signs, so it's they are natural. Okay? No, and again you can compute. You obtain that your yes, maybe you need some b degree. Yes, you have degree of epsilon. It's the number of your resolution, and degree of a. Maybe it's b degree. It's kind of -1, and you have a0, something like this. No, this is Leibniz rule with respect to the sum of two b degrees. Sum of two degrees. It's total degree. But then your bar resolution is b graded. You have grading of number of term of resolution and internal grading of any internal grading of any of these things. This is third term of resolution, but it's graded thing. Okay, it's graded. It's internal grading. Okay. No, and now what about yes, and if you compute such homologies, you obtain Tor, but it's b graded because bar resolution itself also has two grading of I and internal grading. No, it's because for graded models over graded thing, Tor is b graded and X also. Okay. No, and the third situation is when it's differential graded algebra. We have also differential on A. Also non-actively graded connected. No, the same thing, but now I have also differential on A. I have also differential on A. So I have some differential. No, in fact, formula the same, but now maybe it's maybe it's a little bit more convenient to consider two differentials here. I have one differential which of this form, it's bar resolution differential, and another internal differential in each bar resolution term itself. It goes as A, as A, and on epsilon it's 0, so it does not change the resolution number. This is two differentials. On this thing I have two differentials, and they commute with itself because because what is this thing? No, I only need to check what is it on generators. On A, this is 0. This is D. On A, it's just D. No, this is 0. This is 0 on A because this is 0, and this is D of A. It's also some element of A. It's then D delta of A is 0. And on epsilon, it's also epsilon of D. This is unit, and D of unit is 0, and D of this is 0. Okay, it's on any element of A, and on epsilon. Okay, do you agree? So this is it. So in fact, of course I have general differential, sum of differentials. This is my total differentials. It's exactly on A as differential on A and on epsilon by unit. But it's convenient to divide this differential into the two parts. Okay. It's differential graded algebra. It's differential on A. I have some differential on A. It's some given differential on A. Yes, my algebra A now is differential graded algebra. It has differential. Okay. No, it's algebra with some differential.
No, I understand. I try to compute in my head.
This thing.
Yes.
For A. For A.
For example,
This is 0. Yes.
yes.
But dA is also element of A, so this is also 0. This is for any element of A.
Окей.
Я тоже сначала завис, но потом понял. No, okay, and so what we obtain? We have, no, let's do this for some differential module. We have some differential module over your algebra A. And I obtain, in fact, I obtain these bar resolutions. Bar, no, I don't know. Bar A proposition. That if I consider this A, N, it has two differentials. It has two gradients and two differentials. Delta is resolution differential and internal differential. So it's differential, no, because they commute, so it's differential of differential modules. No, what I want to, it's proper free a resolution of n. Again, no, let's check that. Let's, for example, we over field. I don't know, over field or okay. Let's R is field. Over field. No, again, this is resolution because we have contraction. The same bar contraction, it's contraction of this bar differential, What our contraction, epsilon, what's d, epsilon plus epsilon d is identity. So we have contraction of bar differential. So this is exact sequence of free A modules. The second one, what if I consider D here, D epsilon plus epsilon D, what I obtain? What I obtain? No, because D epsilon is 0, but epsilon has degree -1. I obtain that this is minus epsilon D, so it's 0. This means that my homotopy commute with the internal differential, so it can be restricted on, for example, cycles. If I restrict on cycles, I obtain that cycles also contract. So cycles is also exact, so it's proper. It's exact on chain complex and on cycles. It's what we wanted. So from this, I have my epsilon restricts on cycles of my bar resolution. So this is contractible. So on cycles, it's also exact sequence because I have the same homotopy on cycles. Okay. From this property, this homotopy preserves cycles because it's cycle, then it's cycle. If it's yes. If I obtain cycles, then it's epsilon 0. Okay. And also, so this is all. This I obtain. This is resolution, free, and proper. So it's also exact on cycles. It's by definition. What is proper? It means that on cycles it's also exact.
So we proved that this resolution is proper.
Yes, it's resolution by the same argument as before. It's proper. It's because this homotopy. If I have chain complex of differential graded modules, if I consider cycles, I obtain chain complex just of modules, and this also exact because my chain homotopy in fact preserves these cycles with respect to D. These cycles with respect to D with internal differential. I have delta between them. Yes. I have horizontal differential. It's my resolution differential, and the vertical is internal differential. If I consider vertical cycles in each term, I obtain chain complex because it's big complex in fact. But in fact, this chain complex also contracts because my epsilon preserves my cycles. Okay. But what if I consider homologies? Now, if I consider homologies, no, because we overfilled by unit formula, in fact, over ring, if my A and N projective are models, I can assume that my homologies of A and N not projective, but maybe they are flat are models. No, overfilled is not relevant. Then, in fact, what is the homology of something like this? No, for example, if all homologies are flat, or if, for example, if we overfilled, then by unit formula is just the product of homologies. So in fact, homology with respect to is homology with respect to D. Homology with respect to D of vertical of my internal complex of my bar resolution is just bar resolution of homologies. Because of I have commutation of my two differentials, my bar resolution differential also is defined on homologies. And so this is also some chain complex on homologies, and this is exact because it's exactly bar resolution for homologies. It's bar resolution for homologies. My chain complex is bar resolution, and we know that any bar resolution is exact. So it's exact. So my bar resolution is exact on cycles because it's contractible on cycles. And it's acyclic, so exact on homologies because it's bar resolution on homologies. And we know this is exact. So proper we can understand in the sense that it's exact on cycles and on homologies, okay? On internal homologies. So it's good enough resolution. Okay, and so we can use this resolution to calculate differential Tor, for example, and to compute to write down Eilenberg-Moore spectral sequence, for example, because we write down Eilenberg-Moore spectral sequence for any proper projective resolution. Yes. Now we can do this for bar resolution. And what we obtain? Now I just can formulate what we obtained so far. We obtained that homology with respect to our because to compute differential Tor, we consider total complex of B complex. No, this is exactly total complex is what I defined before my total differential. Yes, it's sum of my two differentials. So if I consider my bar construction of for some other module A n with respect to these two differentials. So again, this thing is just something like this. And formula for differentials now it's sum of these two parts. It's bar resolution, differential, and internal differential, some of them. No, this is exactly this differential which acts something like this. It's unit and on A is dA. So you have some signs here. Let me don't write down these formulas. It's the same formulas, but you have one part and another part, and you have signs in both of them, and you have differential of A. For example, let me see. For example, what is M tensor A tensor N? This is M epsilon A epsilon N. It's it's dm tensor. Okay, let's tensor A tensor N plus -1 degree M A N plus minus M and so you have 6 summations, 3 summations of one and 3 summations of another. It's a big differential, but this big differential is total differential with total complex, and its homologies, more or less by definition, is differential Tor. Okay. No, so you have just you have resolution differential and differential on each factor, and Kosul signs. With respect that the bar sign or tensor product has degree -1. So if you interchange d and this, you have also one sign. Okay. And we have Eilenberg move spectral sequence. If we use this resolution, we can, if we use this B complex, we can filter it by, if we use this B complex, this is my n, 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 this is my bar resolution, delta, this is internal differential. I can consider this filtration, yes, no, this filtration with negative numbers, if it is minus n. It's decreasing filtration. Yes, yes. And then from this filtration, we obtain spectral sequence, Eilenberg move spectral sequence. The Tor H A H M H N converges, no, tries to converge. But now, what we have now? For example, let me check the proposition when it strongly converges. No, the abstraction to convergence is that we that this thing, no, only it's second page, but first page, it's just this total complex itself. Yes, no, it's no, it's quotient of this total complex. Yes, it's something like this. No, yes, maybe. Yeah, let me recall. Okay. My first page, no, it's just quotient of this filtration. The quotient of this filtration is exactly elements of some bar associated, some b minus n with internal differential, something like this. And I need to compute internal differential homologies. Okay, but now. Yes, and this is the first page, is this page, and on each diagonal I have maybe infinitely many elements, and so my filtration, maybe has infinitely many elements, and so my quotient, I have infinitely many quotients, I can't control convergence of my spectral sequence. But now, let me assume just that my A is one connected. This means that A0 is F1 is 0. A1 is 0. I have no one-dimensional elements. It corresponds to one simply connectedness of base of Eilenberg homological Algebra spectral sequence. Because if your base is one connected, you can, of course, strictly speaking, this thing is not simply connected, but you can consider homotopy equivalent Cauchy algebra, which is simply connected, if it's simply connected. So if we have simply connected algebra, then in bar resolution, what is the thing? It's kind of this thing. Oh yes, maybe consider reduced bar. Reduced bar is let me say if I consider reduced bar, then on homologies, yes, it's always true. It's also proper resolution. Yes, maybe I need here reduced bar, but it's also true. Reduced bar resolution is also proper, good resolution. And homologies is reduced bar on homologies and so on because I have gradings. Yes, consider bar resolution. What is bar resolution? It's kind of this thing. But if I have no one degree elements, and in A bar I consider no 0 degree elements. So these things, A bar, it starts with degree 2. And if I consider this vertical coordinate is internal degree, this internal degree, no, it's internal degree, or degree with respect to what is that, my differential d vertical of b minus n. No, it's 2 n minus 1, something like this. So in fact, in my chain complex, this first thing, it goes, no, it's kind of this, where it's kind of 2x minus 1. It's concentrated in this part. It's just 0 in the lower part. And so in each diagonal x plus y is 0, or is constant. I have only finitely many quotients. So in this situation, my filtration is locally finite. In each degree, it's finite. So my spectral sequence truly converges. So what's the вывод? Conclusion. What's conclusion? Conclusion that if A1 is 0, then Eilenberg-Moore spectral sequence truly converges to Tor. For example, topological for simply connected base and so on. If it's not simply connected, it's not always true. For example, topological Eilenberg-Moore spectral sequence converge truly if and only if fundamental something like this, that fundamental maybe for example, if we consider topological spectral sequence which computes a homology of loops, then it converges when fundamental group acts nilpotently on each homotopy group, something like this, for nilpotent spaces. And for not nilpotent, it does not converge. It's kind of if and only if, something like this. So no, we need some assumption on fundamental group action. No, for simply connectedness, it's always converges. Okay? Так. So in general, we can compute some of these things by this spectral sequence, for example, by bar resolution. For example, in topological case, so by fields, you can consider bar resolution and obtain some spectral sequence. Now, the last thing what I want to say about bar resolution and the differential is its connectedness with Massey products. For example, let me say this. Let me recall what our situation. We have cochain complex. Let's say we have B complex, cochain B complex, and we have increasing filtration on it. Plus decreasing filtration. Так пишется, decreasing. Okay. What the differentials on the corresponding spectral sequence, как homological type spectral sequence? Now let me recall. We have B complex. We have two differentials, horizontal, vertical, of B degree plus 1, because it's cochain B complex. We have, and decreased filtration on total complex, with sum of differentials. No, sorry. We have B complex, and on total complex we have vertical filtration. No, as in our situation with Eilenberg-Moore spectral sequence. Sorry, we have vertical filtration, decreasing filtration of this sort. It's our situation. in our situation we have p is no, negative numbers, but it's not important here. Okay. Yes, how we define spectral sequence? No, no, yes. What is R cocycles? R cocycles, its elements from P filtration of my total complex such that total differential on C lies in P plus R because it's in decreasing. Okay, remember it. No, what does it mean in our situation? What does it mean? No, what does it mean in our situation? This means what is element of FP filtration? No, it's some. I have my B complex. I have some. No, it's in some degree. In degree P plus Q. So if P plus Q is n, then I have n diagonal. I consider P horizontal. I consider only right part of this. No, so I consider zeros here. And no, some bunch of elements here, it's elements of this. And what is D? No, D is sum of two differentials. I have two differentials of these forms. What maybe I have differentials here, yes? They go to the next diagonal. And I want that, no, what I obtained? I obtained that this is, what I obtained, it's just some elements here. And here I consider sum of these elements, I obtain some elements, and I want that this differential on the next diagonal has zeros for P plus R, to P plus R, additionally to these zeros. Then, if I have such sequence of elements such that sum of differentials are 0 to P plus R, then my element lies in ZR, yes? Okay? This is true? No, this is just a definition. I have some elements on diagonal starts with P. It's elements of my P filtration on n diagonal. My differential is just sum of two differentials. No, I just apply sum of two differentials for each element. I obtain some elements on the next diagonal. And it lies in ZR if my elements, my image of my differential lies in P plus R filtration. It means that it has not 0 only here, but also has zeros to P plus R. Okay, and my spectral sequence, it's exactly PQR modular some image of the previous differential. Oh no, maybe even not that. It's just something like that. It's pi GPQR modular pi BPQR. What is pi? Pi is just projection from filtration to the quotient. And what this quotient is just the first non-zero element. So in fact, what is, for example, what is the numerator of this formula? Numerator of this formula is all such elements in this degree, which can be extended to the diagonal from to the right, such that all differentials are 0 from P to P plus R. It's numerator of this formula. Denominator of this formula, no, it's kind of some images, and then no, it's we can consider some elements here, and then consider image. Okay, it's not important. Maybe it's not important here. But what I want to say that what the R differential here. No, it's kind of exercise for you. But R differential, how R differential acts? It's from PQR to P plus R, Q minus R plus 1 R. What I want to say that what here I have my last element, which is sum of these two differentials is 0. And the next element is not 0, and this is differential of this thing. This is maybe not 0, maybe not 0. And this is exactly differential of this element. It's exactly differential. So I consider, so if I have I consider some element of my B complex. If it can be extended to the right, such that all these elements are 0, are times, then in fact my element survive to R page. If I can extend it to such that all R things, all R differential of the next diagonals is 0, then it survives to R page, and its R differential on these corresponding elements is just the image of this Rth element. Maybe it's also 0, then in fact it survives to R plus 1 page, and so on. Okay?
Why is it like that? The differential is exactly this.
It's exercise from definition of expected consequence of cochain complex. It's kind of exercise. No, it's more or less directly from definition, unraveling of definition, unwinning on definition. It's how Levan Alani likes to define spectral sequences on his seminar, on his spec course. No, it's kind of linear algebra. Yes, it's big complex. It's how people who likes spectral sequences from big complex likes to define it. If it's yes, it's just this definition. You can check that they coincide, of course. Okay. And now let me apply this observation to my bar complex. Eilenberg-Morse spectral sequence. Yes. I want to consider Eilenberg-Morse spectral sequence for trivial modules. So of the following form. Between K and K. It's homology, cohomology of reduced bar resolution. K, H, A, K. It's second page. Okay. Now I just want to define some elements. Let's start from, okay. What we have homology of some differential algebras. Let me have some Massey product. Consider some Massey product of some cocycles in my homology of A. It's some cocycles in A. It's defined in HA, okay? Let's assume. Massey product. And we have defining system. We have defining system. I is just my cocycles. And defining system with this property Dij is sum of I j minus 1 E R plus 1j. It's what we discussed the previous time. More or less the same thing. Okay, let's make clear this. Or maybe let's do this. Okay. Let me just, from this defining system, let me just define some elements in bar construction, in reduced bar construction. My bar construction Okay. But B1, no, what? Okay, lambda. It's from what? B minus n, k, h, A, k. Reduced because no, it's not 0 degree. Yes. Okay. N elements. Okay. No, then B2. No, in fact, it's okay. It's not very hard. It's in fact something like no, and then.
So what do you denote by B? What do you denote by B?
B?
Yes.
B small?
Yes.
Or B capital? The capital is bar
Just
construction.
small.
No, it's definition. Some elements of in bar construction. I want to write down its definition. And then it's some. No, I have so 1, 2. So this is one element lower, degree one degree lower than the previous one. Then I have no. Of course, I have 1, 1. Then I have 2, 3. No, and so on. All things. It's elements with sum in +1. In general, no, it's something like this. BK is just sum of 1A, 1A, I1, K. No, sorry. I plus 1, I2, I n minus k plus 1 n unit. Now, where these elements, where I have n and all these gaps are not greater than k. So it's sum of all increasing sequences of length n minus k with gaps not greater than k. So for 1 and 2, it's the previous ones. If I have gaps not greater than 1, it's exactly 1. It's not greater than 2, it's with n jumps, and so on. For example, I finished by bn minus 1. It's n big jumps. It's sum of 1i, in, I plus 1n. I from, sorry, сбил на нотацию. It's from B2. No, and why we do this? No, it's for exercise. Exercise is the following exercise. You can check. It's combinatorial exercise. What maybe let me. I want to say that in fact these n minus 1 elements lies in diagonal of my bar construction, my total B complex of bar construction. It's B1, Bn minus 1. And an exercise is to check that sum of differentials are 0. So d bk plus 1 plus delta of the previous one is 0. So it's zeros. Now this means that this first thing, B1, survives to n-1 page from the previous discussion. Suppose that the class of B1 in the B1, it's an element of the first page, survives to n-1 page. Oh, sorry, n-1 page. And n-1 differential, it's delta differential of of b minus 1. So, okay, let me clear the board. The n-1 of the corresponding surviving class of b1 on n-1 page is exactly class of delta of bn minus 1. But what delta of bn minus 1? Now this is, if you consider this element and apply delta bar resolution, you exactly obtain Massey product, corresponding Massey product. No, maybe plus minus, modular sign, plus minus class of Massey product. The final cocycle of the defining system. No, and this is what I want to say. So this is what the connectedness between differentials and Massey product. So, for example, if you have Massey product, any non-trivial, any defined Massey product gives you some surviving cocycle, survives to n-1 page, and differential is exactly a class of this Massey product. So, for example, strictly speaking, it says that if differential is 0, then Massey product is trivial. So non-trivial Massey product gives you some non-zero differentials. Maybe in some situations you can incorporate some additional information from this. So it's exactly from bar construction. It cannot be seen from arbitrary projection resolution, but from bar construction, for example, you can see this, that Massey product gives you some surviving cocycle.
What do you mean that this element is equal to Massey product? Massey product is a set.
Yes, you're right. So if differential is trivial, then Massey product is trivial. So any non-trivial Massey product gives you some non-trivial differential. Maybe it's not good, but sometimes non-triviality of some differential is also some information. So what? Okay, that's all what I wanted to say about differential algebra. So now, what time is it? Let's start group homology. If we have the group homology. Let's we have some group, abstract group. Now then, and some, I don't know, and some. Okay, then we can consider group ring, yes? A G module, it's a abelian group with action of this group is the same thing as the ZG module, yes? And so by definition, the homology of group with coefficients in some G module, M is ZG module. It's a abelian group with an action of group G. What is it? What is it? What do you mean? What do you think? Homology of group with the coefficient in some G module. You have group ring. Do you know what's a group ring? Yes? It's formal sums of integer combinations of elements of groups, formal and finite integer. And multiplication from multiplication in group G. So it's a ring.
Okay, perhaps we should take some X and
Or maybe.
No, Tor, because homology is Tor over this ring. No, between M and well, between in fact between trivial Z with trivial G action, and cohomology is X. So for example, exercise. Here I can give some exercise because it's not very hard. First of all, for example, why we consider coefficients Z? We can consider coefficients in any commutative ring, for example, yes, and obtain group algebra, R algebra. Okay, of course you can do this. And if M is not just abelian group, it's just RG module. RG module. No, this equivalent to say that it's G module and R module. Okay, it's R module with an action of G and G module. No, maybe it's important to say that G actions are linear. Yes, maybe it's important. No, it's just RG module. No, then this thing is isomorphic. You can compute them, for example, X over RG, of course, and R and M. So if it's RG module, then you can compute this in this way, and Tor in the same way. Okay. Now let's consider our attention on abelian groups over our minimal ring Z. Okay. Now it's some derived functors of what? Of zero functors. What zero functors? What the zero homology of G? No, by definition it's not by definition. It's from our general thing. It's standard product. But what is this standard product is? What is the standard product? I can consider let me fix some important notations. I have here it's augmented algebra. It's augmented ring. I have augmentation which sends any element to unit. No, so finite sum to sum of coefficients. This is ring homomorphism. It's a ring homomorphism, and so it has some kernel. Its ideal is called augmental ideal. The augmented ideal. What ideal? G, by definition, kernel of epsilon. So it's such sums which sum of coefficients is 0. It's ideal.
It must be the products. It must be M modulo IG M.
Yes. So if I tensor this by M, I obtain this is free model. So it's M Z ZG M. And here image is just EG tensor M. And so we have no exactness on the left, but it's enough for us. So this thing is quotient M modulo image. And the image is, it's something like this. But what is this? In fact, you can check that. Yes, maybe first of all, just as dictation. If you have group rings is such good rings where in fact it's not very important, it's not commutative. If J is not commutative, then ZG is not commutative. But in fact, anyway, it's not very important here, left or right models you consider, because you have automorphism. No, because you have automorphism, G goes to G inverse. No, it's not automorphism of rings, but it's, no, maybe, I say something like this, that it's isomorphism between ZG and ZG with opposite multiplication. If you have opposite multiplication here, these two rings are isomorphic by these things. And left ZG modulus is the right ZG opposite modulus, and vice versa. And by this isomorphism, in fact, no, categories of left and right modulus are the same, and no, exactly the same. Canonically isomorphic. Something like this. So in fact, no, maybe it's important left or right for concreteness, but in fact, if you have left model and you want right model, you can do this. It's not problem of this. Okay, it's just digression. Okay, so here I don't say what's right or left because it's not very important. What is it? In fact, you can check. No, what is this? No, it's abelian group. It's some abelian subgroup. What is set of generators? Maybe you know this. No, if you have sum of elements and sum of coefficients is 0, what does it mean? That I can divide this sum on pairs 1 minus 1. Yes. Okay. And so, no, yes, let me say that. And G, it's I don't know, plus minus 1 G. And if I have, for example, G1 minus G2, then it's just что я пишу не то, наверное, что-то не то. Вот так. And any difference is action of my ring on such elements. So as ideal is generated by these differences, okay? It's ideal, not abelian group, but it's ideal. It's abelian group is generated by something like this. No, as ideal, it's something like this. So in fact, when I quote by this ideal, it's isomorphic to quotient by this ideal. No, so it's quotient of my abelian group by equivalence relation where I identify any element M and its action by any element of G. It's so-called coinvariance of your action.
Why is it true?
Mm-hmm.
Why is it generated? Because you have G2 times the element of...
Yes, as abelian group, it's generated by just such difference, okay? Because any sum where sum of coefficients is 0, you can consider you can rewrite as sum of such differences, okay? You're right? Do you agree? No, but any such difference is just G H. No, so if I consider these elements generated by ideal, so it's generated by ideal, as for example as left ideal. I consider such elements and then can multiply them by any elements of my ring because it's ideal. It's ideal. It's left ideal, for example, or right ideal because it's not a pot. It's two-sided ideal. No, so yes, it's quotient by this. It's you identify M and action on M by any element of G. It's so-called coinvariance of G action. No, and what is the zero cohomology? Zero cohomology. It's home from Z. No, it's more. I think it's more obvious. It's just home. Well, it's notable for you that I write here equality, not isomorphic, because no, strictly speaking, it's kind of isomorphic, but it's canonical isomorphism. From Z to M over ZG. No image. No, here image is defined by image of unit, and here action is trivial. So image of unit can be any element of M in each action is trivial. So it's exactly the set of elements in which action is trivial. It's invariant. It's fixed points of my action. M such that Gm is M. This is quotient Gm is equal to M. So I have two functors from my G modules to abelian groups, invariance and coinvariance. And in fact, they coincide with tensor product and Hom with trivial product. And so my homology and homology is derived functors for invariance and coinvariance. Okay. Может быть, сегодня давайте мы тогда считать будем в следующий раз, а сейчас давайте закончим топологической интерпретацией. Да? Значит, let we have covering G covering. So it's a regular covering with its action Y is a quotient by free properly disconnected action of G on X. Okay, so it's covering and it's coincides with action by some with quotient by some group G. Okay. What you can say about singular chains of X, G X on X. Okay. Then G X on singular simplexes on X. So in fact, this is the G module. Do you agree? Because you can consider any simplex, singular simplex, and then X by G, you obtain some new singular simplex. It's action on set of on singular simplex, and by additivity, it's action on abelian groups generated by singular simplex. Okay. Now I claim that in fact this is free ZG module, and this is as ZG module is ZG tensor with Cy. It's free abelian group, and this is free module exactly with the same basis. So it's extended free module. Do you agree with this? No, it's because if I consider any singular simplex in X, singular simplex, for any n, if you wish, then I consider projection. So I obtain some simplex here, but any simplex here has exactly here lifting. Okay. Any simplex to Y has exactly not exactly. It's in natural bijection with G. You can consider any one lift and then X by G, and you obtain exactly all lifts because the simplex is simply connected. It's contractible. No, and this gives you bijection between singulars here and a kind of G orbits of simplexes here. And so you obtain that any simplex here is G of gives you in fact bijection between simplexes singular simplexes of X in bijection with set of G singular simplexes of Y, where G in J, something like this. It is bijection on basis, and from this we obtain this isomorphism of free abelian groups. Okay, and so if I want, if I have, so if I have what I want to say. For example, if I consider C, yes. Now consider EG, BG, universal cover. G is discrete, so in fact it's Eilenberg-MacLane space KG1, and this is it's universal covering. Okay. No, then, in fact, I have this thing. In fact, you can check that because of EG is contractible. So this chain complex is also contractible, because from topology you know that contractibility of topology space gives you contractibility of singular chain complex. It's homotopy invariance of singular homologies, exactly this thing, okay? Because when you prove homotopy invariance of homology, you prove that homotopy between spaces give you homotopy between singular chain complex, okay? So because EG is contractible, this thing is also contractible. This means that if I consider augmented complex goes to my to Z over Z, it's exact, it's acyclic, it's contractible. It's acyclic, and in fact this is complex of ZG modules, and these ZG modules are free ZG modules. So this is free ZG resolution of Z. It's free ZG resolution of Z with trivial action here. So you can consider any module, G module, tensor it and obtain homologies. So topology gives you just a free resolution of Z, what you need to compute homology next. For example, homology of group then can be calculated by homology of this tensor product of CEG, tensor over ZG with some module M.
So could you repeat how we use that the complex is contractible?
Yes.
No, complex contractible means that it's acyclic, it's exact.
Okay.
So its resolution is exact. No, and we know that these modules are free ZG modules. No, and also you can check, in fact, of course, you can check that these differentials are maps of ZG modules, but it's also true. So it's free resolution of ZG modules, and we have something like this. And cohomology it's cohomology of Hom, yes, Hom. So no, it's so-called homology with local coefficients. If you have some G module, then in fact you can in fact this cohomology is just homology of the universal cover of KG1 and with some coefficient. No, for example, for simplicity, if M, if M, the last one, if M is trivial G action, this means that any element acts by identity, okay? Then, again, what is this? What is this? What is this? What? Maybe no. Sorry. Maybe. Just 1 second. Just. No, what I want to say something like this: that that C star EG tensor over ZG with M. But C star EG is free module. So in fact, we know that this is kind of C star BG tensor ZG. And then I tensor it over ZG with M. No, yes. No, this always obtain something like this. It's always just this thing. Sorry. Да-да-да. And home. No, home from free module.
Wait, why is it true? Why can we insert the G like this?
Okay, let's consider home, for example. What I have home from free module. It's free module with basis BG, and then there's ZG. No, you know that map from free module is the same thing as map from basis. So I can clear here and obtain the thing.
This is kind of obvious.
Well, this is dual thing. It's if maybe it sometimes happens, but dual is not obvious. But no, this is the same thing in fact. No, this is over any ring. You have modules. You have extension of rings, and then over ring S, and you can divide it.
No, this is okay, but you changed ZG to Z.
Где? What?
Wait.
No, we proved that they think it's free module over this with yes, it's free module over Z with this basis. Basis quotient. Uh-huh.